Hello and welcome to this lecture. We've been looking throughout at basic concepts of probability. Once again, these are very important rudimentary basic ideas. You have to grasp them really well and you have to learn how to use them. That's what's most important. Most people just listen to something and think, okay, I know this, I understand this, I understand this. But till you put it to use, till you solve problems with it, really you have not understood, or you don't know how to apply it. So it's as good as not understanding it. So there's no understanding without the associated action that comes along with it, right? So it's very important that you practice, and there are enough practice problems that will come out for every lecture. So I hope you enjoy the practice as much as listening to the lectures. So we've defined all the basic quantities involved in the probability space, right? We are studying about the probability space. There's an experiment and it has outcomes, and after that we have the mathematical theory, which starts with the sample space, which is a set of all outcomes, and then there are these events, right? So events are subsets of the sample space, and then there is this probability function which associates a value between 0 and 1 for every event that you have in your probability space. So this is the group of three things, triplets if you will, that make up a probability space: the sample space, the collection of events, and the probability function. Okay, and there is a restriction, there is like a condition or an axiom that we impose on the probability function. Relatively simple axioms, we saw it before. The entire sample space itself should be assigned a value 1 for probability, and if there are two disjoint events and you take their union, the probability of the union should be sum of the probabilities of the individual events. These are the two axioms, and we were trying to use that axioms, and it seemed like it was a little bit confusing to use. So what we are going to do is start with the axioms and make some very useful deductions and study some important properties of the probability space. So that's what we'll do in this lecture. I'll put out 4 or maybe 5 properties for the probability space, and that makes working with probability space so much easier. And these are all deductions, okay? So these are not axioms. The axioms are only 2, and we will logically prove these results that we'll see. You'll see they are very simple results in some sense. Okay, so let's get started with the properties. We will only see the properties in this lecture. In the next lecture, we'll see applications of the properties. Okay, so let's get started. Okay, I just did the full recap. I'm not going to do the recap again. So this is the recap slide of where we are, and we're going to look at the basic properties of the probability space, and you'll see it's very useful when you work with the probability space to know all these basic properties. Okay, so here's the first property. I will call it the empty set property. Probability of the empty set, which we will denote as this phi. Okay, so it's a Greek letter with a circle and a straight line on top. It's the Greek capital phi. It denotes an empty set. Okay, so a lot of people ask why mathematics is considered very difficult, and I'll say one of the reasons is they choose to use Greek alphabets. Okay, you know, if you say things like A, B, C, it seems quite easy. If you start saying alpha, beta, epsilon, and all that, suddenly it seems like it's confusing. And the Greek thing could have been avoided. If you think this phi is very confusing, simply use empty set all the time. It's perfectly fine. It's just a notation for empty set. Okay, so the first property. Now this is not an axiom, remember, this is a property. There are only 2 axioms. We will prove this property using the axiom. It's a very simple proof. You'll see how easy it is. The property says the probability of the empty set equals 0. Okay, so the probability function assigns a probability of 0 to the empty set. So if you remember, the axiom said probability function assigns a value 1 to the entire sample space. Now to the empty set, it assigns a value 0. Okay, so let's see how to prove it. I'll quickly go through the proof. The proofs are not so important in this class. You will never be asked to prove anything. Okay, I promise you that. You'll only have to apply it. But I think for those of you who are interested, you can sort of see where the proof comes from, and it's very simple actually. It's very easy use of the axioms. Remember, we're only going to use the definition and axiom. We cannot intuitively say, intuitively it's clear that the empty set has nothing, so the probability should be 0. That is not a proof. Proof is you have to use logical deduction starting with the axioms and go to the exact statement that you want to show. Okay, so this is how a proof would look. You look at the complement of the empty set, that is the entire sample space S. Okay. So, that is the first observation. The next observation, maybe I should show you with this pointer here. Okay. So, the first observation I have is the complement of the empty set is the entire sample space S. The next observation I have is this guy, phi and S are disjoint, right? Right, it is very easy to see that phi and S are disjoint, empty set is disjoint with everything else, is not it? So, clearly phi and S are disjoint, and you also observe that phi union the sample space is the sample space. Okay. So, these are three critical observations involving the empty set. The empty set's complement is the entire set S. So, that clearly means that the empty set and the sample space are disjoint, and interestingly, if you take the union of the empty set with the sample space, you will get the sample space. So, these are easy things to think of, and now we are ready to use axiom 2. Okay. So, you have two disjoint events and we know their union. So, let us use axiom 2. What does axiom 2 tell us? Probability of phi union S is probability of phi plus probability of S, right. So, these are disjoint. So, what is phi union S? That is S itself. So, probability of S is probability of phi plus probability of S. So, that tells you probability of phi equals 0. Okay. So, notice how the axiom was used, and I did not appeal to any intuition or something. I used the axiom and then just algebraically proved the result for you. Okay. Once again, I am not going to spend too much time on the proofs in this course, but let us once again go back to the intuitive feel for this property. It is very clear that any probability function better assign the value 0 to the empty set. There is really nothing in the set, so there is no way that event can occur. So, it should have a probability 0. Okay. So, let us move on to the next property. This is what we call the complement property. So, once again, this Venn diagrams for illustration is quite useful. At least you can picture what this means. You have the sample space S, the entire sample space has a probability of 1, and then you have an event E. Okay. The event E is a subset of the sample space and it has some probability P of E. Okay. And then you have the complement of E, right. What is the complement of E? It is everything else other than E. Okay. So, what is complement? I mean, it is sort of logical that the complement should be an event, right. So, if an event occurred, the E complement did not occur. If the event did not occur, the E complement occurred. So, doing complements, doing unions, doing intersections are natural processes in a probability space. So, if an event E exists, E complement will also be a proper event. It has to be in some sense, right. So, those are things we will assume about events, otherwise you just get stuck, right. So, the basic operations that we do with events should be all possible, right. So, that is something we will take that as true. Okay. So, you have an event E, you have its complement E complement. So, this probability function P, if you evaluate it on E complement, it should be equal to 1 minus P of E. Okay. So, notice that this places a restriction, this property gives you something very useful about what the probability function does. Okay. If you put some probability to the event E, let us say for instance, if you say event E is 30% chance of occurring. So, what should be E complement? What should be the probability that E did not occur? It should be 70%, right. So, 1 minus P of E is a perfectly intuitive result. Okay. Nobody is going to be very surprised if you make this state this result, but one can prove it very rigorously from the axioms. Okay. I will just quickly go through the proof. Everything starts with E and E complement being disjoint and E union E complement being the sample space S. And then you use axiom 2, you get that P of S is P of E plus P of 1, P of E complement, and then you use axiom 1 to get P of S as 1 and you are done. Okay. So, once again I want to point out a couple of quick things. One is once you have an event E, why should E complement also be an event? These are things we will assume. We will assume the events are like that, natural operations on the events give you other events, things like unions, intersections, complements, all of that give you other valid events. You cannot say that those are not events because one occurs, the other event also occurs. If you have two events A, B, if you say A union B, either A occurs or B occurs and then A union B will occur, right. So, it is clearly a valid event in the sense of probability space. So, you should have those kind of things possible. And so, this property gives you something very useful. So, this is the second property. First property was empty set. The probability functions always assigns the value 0 to the empty set, and if it assigns a value P of E to an event E, the E complement event is 1 minus P of E. Okay. So, it is very clear and it's very simple property. Okay, so it will all sound very simple, and as you keep listening to it, you'll be nodding your head saying, yeah, this sounds easy, this sounds easy. But once again, you'll see when we want to apply it in a problem, you will always get confused about what to apply, what not to apply. Is this property useful? Is that property useful? So pay attention to how the intuition behind the property. But let's see, when we use it, we'll see how well you have understood these properties. Okay. Next is what I'm going to call as a subset property. So if you have two events and then one is a subset of the other. Okay, so we'll assume two events, one is a subset of the other. What does it mean to say subset of the other? If E occurred, F definitely occurred, right? So E is inside F. Okay, so if E occurred, F definitely occurred, but F can occur without E occurring also, right? So this picture here, the Venn diagram here, sort of shows how the events and sort of look in a Venn diagram. You have the entire sample space S, the big oval here, and then you have a smaller oval which represents the event F, and then you have an even smaller oval inside of F, which is the event E. Okay, so this clearly shows E is a subset of F. Okay, so if you have something like this, one can define something called F minus E. Okay, so this is something you might have seen before in set theory. If you have not seen, let me define it for you. F minus E is basically the elements of F which are not in E. Okay, so if you look at this picture here, everything inside E is inside E. What is F minus E? The things in F, right? All these guys which are not in E. Okay, so that is F minus E, and believe me, if F is an event, E is an event, F minus E will also be an event. Why is that? Because it is the same as F intersect E complement. Okay, so E complement is everything outside of E, and if you take F intersect E complement, you get a valid event. So this F minus E is also a proper event, right? So it's all reasonable to assume F minus E is a event. So this probability function will assign probabilities to F, to E, and F minus E. Okay. So what does this property tell you? This property tells you these three probabilities: the probability of F, right, the probability of the entire F, and then the probability of E, what is inside this small circle, and then what is in F that is not in E, right. It's clear, sort of intuitive, that this P of F should be equal to P of E plus P of F minus E. If it's a reasonable probability space, this should be true, and that's a property that holds here. Okay, so we can prove this property. It's not very hard to write down and prove it. I have a proof here. It just relies on E and F minus E being disjoint and the union being F, right. So, and then you use axiom 2, you are done. Okay. So, in particular, notice what this implies, that this P of F is always greater than or equal to P of E. Okay. Now, this is quite important. I want you to think about why this is important here. So, if you have P of F to be equal to P of E plus something else. See, this is a positive quantity, right? It is a probability. Probability is only between 0 and 1, right? So it's a positive quantity. So you take P of E and then add something to it, you get P of F, which means P of F is greater than or equal to P of E, or P of E is less than or equal to P of F. Okay, so these two properties are very useful. When you have a subset, the events will sum up like this, and that's a property that the probability function satisfies. Okay, more than anything, quite often you will have an in a complicated problem, you may have an event which is very difficult to calculate probability for. Okay, so what people do, a very useful trick that they use is, they will find a bigger event which contains this event, and for which you can easily compute the probability. Okay, so then you don't know the exact probability of E, but at least you have an upper bound, right. So if you have, instead of finding E, if you find probability for F, where F is a bigger set than E and you can easily compute it, then even though you don't know P of E, you know that P of E is at most this. Okay, so usually that's a good thing to have, right. If you don't know the exact probability, like you don't know if it's 10% or 12%, but you know it's less than 15%, that's good for you, right. So that's the sort of thing that people use these kind of results for. Okay, once again, let me summarize. There are three properties that we have seen so far. The empty set has to be assigned a probability of 0 by the probability function. That's the first property. Second property was the complement property. The probability of E complement is 1 minus probability of E, very intuitive once again. Third property we are seeing is the subset property. If you have two events, one is contained inside the other, as in if one event happens, the other event is definitely supposed to happen, right. E is inside F. then P of f is P of E plus P of f minus E. F minus E is sort of another event. We saw why that should be an event, right? It's f intersect E complement. Okay. So that's subset property. Hopefully this is clear enough to you. The proofs you can see are very simple. There is 2 or 3 lines and they come repeatedly use this axiom 2 and axiom 1, and you'll see how it's very powerful to get this result. Okay. Let's go to property 3a. Okay, so it's very similar to 3, but it's 3a because now we're going to look at 2 events, but one may not be contained in the other, right? So here is a picture here. So you can contrast it with the previous picture. You have your sample space S, and then there is this event F, and then there is another event E, and these 2 events sort of overlap, but one is not inside the other, right? So these are 2 different events. So this is how they look. Okay. So now what you can do here is you can look at E intersect F. Notice this E intersect F, it's here, right? Even though E is not a subset of F, E intersect F is a subset of F. Okay. And likewise E intersect F is also a subset of E, but at least E intersect F is a subset of F. So that's the starting point for this proof, and you can see quite easily that P of E is going to be P of E intersect F plus P of E minus F. So E minus F is whatever is in E which is not in F, okay, right? So that's E minus F, right? So E minus F is whatever that is in E which is not in F. So all these guys, all of these guys will be in E minus F, okay. So just the subset property applied to E intersect F and E will give you this result, okay. And you can think about why this is true. It's sort of intuitive as well, right? So probability of F is probability of E intersect F, both E and F happening, and then F happening alone without E, okay. Either both E and F happened or F happened without E, okay. So this is these are all very important properties, I mean we will use these sort of intuitively to compute probabilities. I'll try and show you some examples where we'll end up using these things intuitively. As we calculate more and more complicated probabilities and more complicated scenarios, you will use results like this, okay. So you want to find a probability for an event F, okay. You will find some other event E and find its intersection, find the probability of that, and then go to F without E, okay. So you will keep doing this again and again. You can do these things for simplifying your work, okay. So that's property 3a. Finally, we come to union and intersection, right. So we've been talking a lot about union and intersection, and here is a very simple and yet powerful, elegant property which connects the probability of union and intersection to probability of the original events, okay. So this is a very important property. Supposing once again you have 2 events EF, okay, inside a sample space S. The probability of E union F, okay, E or F. What is E union? Once again, it's E or F. Either E occurred or F occurred. If you want the probability of that, it is the probability of E plus the probability of F minus probability of E intersect F, okay. So how do you understand this result? I mean, there is a proof here. I'll encourage you to look through the proof. I'm not going to discuss the proof in more detail, okay. But how do you understand this result? Okay, so here is E intersect F, okay, we can do like a proof by Venn diagram. E union F is this whole area, right, isn't it? Now what is P of E is this area, and what is P of F? It's this area, okay. If you do P of E plus P of F and you want P of E union F, what would have happened? This intersecting area, right, E intersect F would have gotten added twice, right. It would have gotten added once in F and twice in E. So you have to add P of E plus P of F, and then you have to subtract P of E intersect F, which is what I am doing here. Then you will get P of E union F, right. So it's sort of intuitive, and I sort of gave you a rough proof by Venn diagram. But if you want an exact proof, here is an exact proof, and you can go through this. This is not very hard to prove. You can basically write E union F as a disjoint union of 3 things, and then you will get the result quite easily, okay. So hopefully the results are interesting to you, the properties are intuitive to you, they are not very surprising. It's this lecture just sort of mostly notation and sort of dryish lecture talking to you about the properties. In the next lecture we are going to apply it in multiple problems. So you'll see, you can test whether you grasp the properties properly or not, you will be able to use it or not. We will do that in the next lecture, but hopefully these properties are clear. So, let me once again quickly recap. You had the two axioms which are always true, right, for any probability function. This entire sample space is assigned a probability 1. If you have two disjoint events, the probability of their union is probability, the sum of the two probabilities. Okay. So, this union and intersection result is sort of an extension of the axiom 2 to the general case where E and F are not disjoint, right. If E and F are not disjoint, if E and F are disjoint, probability of E intersect F is 0, right. Why is that? E intersect F is a null space. So, this goes to 0. So, you get the original axiom 2, right. So, here this is a generalization of axiom 2, isn't it? If E and F are general events, then E union F is P of E plus P of F minus P of E intersect F. Okay. So, this is union and intersection. We had the empty set property, we had the complement property, right. Probability of complement of an event is 1 minus probability of the event. Then we had the subset property, then we had the difference property, right, difference and intersection property. Then we had the union and intersection property. Okay. All right. So, that is the, I believe, the end of all the properties. In the next lecture, we will look at how to use these properties and start computing the probabilities of different events in probability spaces. How do you start working with probability like spaces? That we will do in the next lecture.